Hello, good evening everyone. Welcome to the 7th live session for the course Geomorphic Processes, Landforms and Landscape, which is taken by Professor Javedan Malik from the Department of Earth Sciences, IIT Kanpur, and myself Ananya Mukherjee. I am a PMRA Fellow, PhD student in the Department of Earth Sciences, IIT Kanpur. So we've been learning about geomorphic processes and geomorphological features, uh, in the course till now. Okay, so we have finished learning about the changes in landforms and formation of different landscapes due to the action of natural agents like river or water. We also learned how tectonism or plate tectonics itself can cause geomorphological features to form or change previously formed geomorphic features. Then we also learned how glaciers can form such landscapes, as well as what are the kind of different landscapes and landforms we see in the coastal environment, okay, due to the wave action of water. Okay, so we are almost done with the course content per se. Okay, so today we will be dealing with aeolian landforms, or geomorphological features that are created by the action of wind. Okay, so what is aeolian geomorphology? It is actually the study of landforms, geomorphic landforms, which are formed by the action of erosion, transportation, and deposition that is done by wind blowing over the Earth's surface. So usually, these processes are active in regions which are actually dry in nature. Okay, mostly, or where the moisture is a bit low, and whereas the supply of sand is high. Okay, like sediments or sand size sediments are high. Okay, so these can happen in coastal zones or hot and cold deserts. Okay, so you have cold arid regions also, you have hot arid regions also, and large expanses of lands, either agricultural field or even barren land areas also. Okay, so wind erosion and transportation and deposition, all of these can happen in these areas. Okay, yeah. So usually the kind of sediments that are transported by wind are finer in size, like you have clay, silt, and sand. Okay, so these are the sediments which are mostly transported by wind after they have been eroded and then they are deposited. So some of the examples of aeolian geomorphic features could be sand dunes, lowest deposits, ventifact, yardungs, deflation hollow, blowout, desert pavement. Okay, so we will see some of these in the coming slides, how they are formed and which process of the aeolian geomorphic process, which of those are actually forming such landforms. So before we go into that, we will try to understand the major region or the most prone region on the earth where which is where you have most of the action of wind happening. Okay, where most of the aeolian geomorphic features are formed. So we have seen, or it is seen that 1/3 of Earth's land surface is desert. Okay, so usually deserts are formed where you have very low rainfall. Okay, so these are arid areas. They cannot support vegetation, and also the population of living beings, like people, humans, and animals are very low in deserts. Okay, because of the inherent dry and hot climate that is prevalent in such areas. So but it can be hot and cold. Okay, so mostly what we are going to study in aeolian geomorphology, we are going to focus on the hot deserts. Okay. So, and usually these areas are covered, vastly covered by sand, or you will find coarser rock fragments, or you will have exposures of rocks, okay, jutting out at places in the desert. Okay. And so, how would you classify these desert areas? Mostly these desert areas actually, occur in the subtropical latitudes. Okay, so like it will expand from the equator also, but and then it will move up to the subtropical latitudes. Okay, so Peveril Meggs actually classified the desert regions into three categories. So you have extremely arid. Okay, these are based on the these categories are based on the amount of precipitation that the regions are receiving on an annual basis. So extremely arid lands have at least 12 consecutive months, that is one whole year they can go without having any precipitation, these areas. Then you have arid lands which have less than 250 millimeters of annual rainfall, and you have semi-arid lands which have mean annual precipitation of between 250 to 500 millimeters. Okay. So these classifications are based on the amount of precipitation the areas receive, and these areas, extremely arid, arid and semi-arid, these regions are the regions where you will find most of the desert across the earth's surface. Now, how are these deserts formed? Okay, so one of the most you can say the most common way that a desert is formed is by the orographic effect. So what is the orographic effect? Suppose you have evaporation is happening in the coastal areas and the oceans. Okay, so due to that, the warm moist air is actually going to rise up over there. Okay, so the atmosphere absorbs the moisture and it starts moving inland. When it is moving inland, okay, and if it meets a mountain range, so what is going to happen is the moist air, the warm air is forced to move up. Okay, because it is interacting with a elevated area like a mountain range. So the air is getting colder as it is rising up. Okay, so it is going to cool, and it will not be able to carry the moisture that it was carrying with it. Okay, what happens then is that condensation happens, and you will receive precipitation over there. It will be either rainfall or snowfall, okay, depending on the region that is there. And once the precipitation happens at the place, okay, that is the upwind side. Okay, so this is the upwind side, this is the downwind side. Okay, this is the downwind side, this is the upwind side. So the rainfall or the precipitation is happening in the upwind side. Okay, so once it is happening in the upwind side, the air, the moist air that was there, okay, it has lost the moisture, and this precipitation is called orographic precipitation. And the effect that we see because of this draining of the moisture in the upwind side, and then the air is moving towards the downwind side, okay, to the other side of the mountain, and this is the orographic effect, okay, which is causing the desert formation of desert in the downwind side. So all the vegetation and everything is happening over here. Yes, Sora?
I have a question here.
Yes.
Uh, this orographic precipitation is okay, but if some area is receiving less rainfall, does it necessarily mean it is forming desert?
No, it is not necessarily forming, a desert. It could happen in many other. It won't be a desert, but it would be maybe a drought prone area. Okay, so like you have Vidarbha region in Maharashtra. Okay, so per se it is not a desert, right? But
Yeah.
we know that it is drier. That is also because you have the Sahyadris, okay, in the Western
Yeah, so
Ghats.
in this example which
Yeah.
we are seeing, if we are saying that orographic precipitation is actually the reason for which on the leeward side
It
we
is
can have
one of
desert.
the common
So I
Okay.
was under the impression, so if you go for the Indian Thar Desert,
Yes.
um, this is desert, right? So
Yeah.
it is on the leeward side. So what would be the windward side of it?
I think it's because of the the effect of Himalayas when the northeast monsoon is happening. See, southwest also it is not receiving, that area is not receiving the rainfall. Okay, southwest it's going to turn and it is actually giving the rainfall on the western part of the India. Okay, so it's not like moving towards that side. That area, okay, I think over here, yeah. So
Mm-hmm.
when the southwest monsoon winds are going, okay, so they kind of travel like this.
Mm-hmm.
Okay, so all the moisture is kind of drained here, and because of the Himalayas, this is the part where you are getting the rainfall. Then you have this desert over here. Okay, this desert is forming over here. Now there are also these southwest winds are actually not even traveling this side anymore. Most of them are draining on this area. Now when you have the northeast monsoon winds, okay, again it's coming from here, okay, but again because of the Himalayas it's not going to drain anything over here. There is no precipitation in this area. So it is one of the most common ways, and because you can see that most of the rainfall areas are going to be near the equator itself, and because of these some over here you have the Himalayas, the Eurasian plate, okay, then you also have some, I can't recollect, there are some mountain ranges even on this side. uh, I cannot recollect the name right now. So there are mountain regions even there, because of which the these winds, if there are coming from northeast side, or maybe the southwest monsoon winds is trying to reach here, it is not going to reach the Thar part.
So we should see some windward side also, but I can see the entire Thar deserts moving from India to Pakistan and all the way to Middle East. So I don't see any windward side of it. So that was my question. If orographic precipitation is the reason for the formation of desert, for Indian context, where should be the windward side of it?
The windward side is going to be on this side. Oh wait, I'll just erase this and I'll mark it.
That's fine. We can carry it later on also.
Yeah.
We can continue.
So
I'll
this
note
is
it down and
this.
send it across.
Sorry.
I'll note it down all these things and we'll send it across. Maybe we
Yes.
can discuss.
Yes.
Fine.
Yes. Sure. I have actually sent a Google form over here. Okay. So
Mm-hmm.
if any of you have queries, any of the queries in today's lecture or in the previous classes, you all can put the doubts and your queries in this form, and I will try to cover up most of the the general ones that are there in the revision class in the next week.
Okay.
Okay,
Thank you.
no problem. So in the sense of the orographic precipitation, okay, so we are talking that due to the presence of the mountain ranges, the precipitation is happening on the upwind side of the mountains, and the air that is moving across the mountain ranges have now lost all the moisture. Okay, they, it is cooler, but it is also dry air now. Okay, and then again as it is descending, okay, so from the elevation it is now descending, so as it descends it's going to get warmer. Okay, and because now there is no moisture in the air, okay, so there is no cloud formation, there is no condensation, and so this area will no more receive any precipitation per se. Okay, so this is actually called, this area is called a rain shadow. So the rain shadow region is actually usually the areas where you will find deserts forming. Okay, so this rain shadow region, okay, it could maybe receive rainfall if there is any moisture left in the the air that is coming through the mountain ranges. Okay, but it's going to be very low. The annual precipitation is going to be very low in that region, and since there is no moisture, the amount of vegetation is also lower over there, and the since there is no moisture, you will not have much organic matter itself in the soil. Okay, so that again is not going to support the vegetation, or it's not going to support any sort of any kind of livelihoods. Mostly livelihoods will be difficult, okay, in these places. So what you are left with are sand and rocks. Okay, so you will have all the material probably, that is coming down from here. Okay, and since these don't hold any moisture over here, okay, so they will be probably, just sand and rocks over there. And because there is low humidity, so these places could get extremely hot in temperature. And but the temperature difference between the day and the night is going to be very drastic. Okay, there is no moisture in the air. So, and there is the there's a term I'm forgetting. Okay, so the temperature variation that we see in the day and night is going to be very drastic. You will have very hot days, and you will have very cold nights. So these are some of the characteristics that we see in rain shadow regions, and most of the deserts that are forming are actually falling in these rain shadow regions. Okay, so this is one of the most common ways that deserts are forming on the earth. So now we understood that these are the areas where deserts are the areas where the wind erosion or wind transportation and deposition by the action of winds is kind of common. Most widespread geomorphic process in these areas is going to be done by the wind. So we'll learn about the yeah. I'm sure this. Yeah. So what is wind in general sense? Wind is a moving mass of air. Okay, so it blows over the area. Okay, and usually it is a dynamic system, and the movement is due to pressure differences in the two regions. So the driving force is going to be like one place you have low pressure, and the other area you have a high pressure. Okay, so that is going to allow the wind to move from one place to another. And greater the pressure gradient, greater is the force on the air, and the wind speed is going to increase because of that. Okay, and when the wind is blowing over the earth's surface, it can circulate, and it can also transport some material because of the speed that it has. So that is why wind is one of the greatest, or one of the most active agent which can cause land erosion and transportation of the sediments. Okay, and these are very effective in regions of arid and semi-arid regions. And as moisture laden air is not going to flow through an area with greater speeds. Okay, because it's heavy, it's laden with moisture, so it cannot more humid air, or is not going to cause any sort of erosion in that sense, how much the wind in a dry region can cause. Okay, so air near the surface gets heated, it rises, then cooler air comes to replace the hot air which has just risen above. Okay, and this movement is going to generate the occurrence of the winds. And that is why the wind, because it's moving, it can transport, and when it's transporting, the material that is caught up in the wind now, that is getting transported, can erode the the other rock exposures maybe, or or help in transporting more similar sized sediments with the wind. And later on, where either there is a drop in the pressure, or there is a drop in the elevation. Okay, so what will happen is the transported sediments can, they drop down, or and they can get deposited in areas. So arid regions are the best examples, of places where wind erosion is the predominant kind of geomorphic process. So now we understood that, how winds, the inherent way that the winds move is actually causing the different kind of erosion and erosion, transportation and depositional acts. Okay, so it is primarily the way the winds will erode. Okay, it will primarily base on wind velocity and surface roughness. Okay, so if the wind velocity increases, the erosive power or erosive force of the wind will also increase. Okay, so it's general physics. Okay, so if the wind is it's the velocity of the wind is higher, it can take up a lot of, finer sediments with it, or even coarser sediments with it. And the sediments itself, if they meet an obstruction in its path, it because of the high velocity that it is moving with in the wind. Okay, it can cause the erosion to happen. So that is why we say fast winds are going to, erode much more than slower winds. And how the roughness of the surface is going to play is that, boulders, trees, buildings, smaller, anything that is kind of, obstructing the wind, or it is holding on to the land, it is holding on to the sediments. Okay, so it is not going to, it is going to increase the friction between the wind and the surface that it is meeting, and it is going to decrease the wind velocity. Now if the wind velocity decreases, it cannot transport, it cannot erode, okay, with that much capacity anymore. So vegetation, having vegetation is going to kind of, decrease your erosive power of a wind. So one of the important ways that, winds erode is called deflation. Okay, so what is deflation? Deflation is actually lifting and removal of fine dry particles of silt, soil and sand by the blowing wind. Okay, so the wind is blowing, and the area, okay, the area has all different sizes, sediments and rocks, fragments of rocks and outcrops. Okay, so what the blowing wind is going to do is, it's going to pick up the smaller sized particles, the finer particles, and it is going to take it ahead along its path. Okay, so what is left back are the bigger, coarser grains, which could not be taken away by the wind as the velocity, depending on the velocity of the wind. Okay, so at some places, sudden, gusts of wind, or, streams and jets can take a lot of sand with it. Okay, it will just blow out the sand. If you like, take some powder in your hand and you kind of blow on it. Okay, so you will see, not, if you take a heap of it, there is a lot of it, so you will see the entire amount of powder has actually not, just blown away. Okay, one place where it was concentrated, suppose a blow was, the concentrated at one place, only that place the powder is going to just move apart. Okay, it might get scattered to the other areas, or it's going to move ahead and get and, drop down in further away from you. Okay, so that is what happens when winds blow, and then there are blowouts of the sands and the rock particles. Okay, so the first what happens is, the blowing winds are going to clear the fine grained material and the sand sediments. Okay, sand sediments, and what you are left with are the coarser fragments. So when, there are large areas where you can see these coarser fragments are there, and it is dry in nature. Okay, and like it's in the arid region, arid climate. Okay, so these vast expanses of lands can be called as rocky deserts. Okay, then the other way that erosion, happens is by abrasion. Okay, so abrasion is nothing but due to the frictional action between the sediments that are carried by the wind and the obstruction surface. Okay, so there is friction, and what happens is when the sediments are moving across the surface, it's going to scrape the surface of whatever outcrop is present over there. Okay, so this happens during the when sediments are being transported by the wind. So this process can also be correlated with the process of like corrosion. So what happens is when the wind is striking and obstructing outcrop, the sediments are kind of scraping the scraping the surface. Okay, it might even pick off chunks of the already loosened fragments on the surface. So it is going to keep it will take up those sediments also with it, and that is why this process is also called corrosion. Okay, and it can lead to formation of grooves and scars, and it can even polish the rock surface. So that is how abrasion takes place, and that is also one of the most important processes of erosion that is done by the sediments transported by the winds. So now since we saw that wind is such an active it has such active erosive powers. Okay, so some landforms are very characteristic of this these wind erosion processes. So as I explained deflation, where you have the blowout, sand blowouts. Okay, which are an area has lost the fine particles or the sands from one place to another because of the blowing wind. So these places can be called as deflation basins or hollows. Okay, they are they are also called deflation blowouts. And what happens is the removal of the finer sediments or by the wind that is going. So you can see over here that sometimes these deflation hollows, okay, they intersect the water table, and you can see that if the the water will seep over here and it can create oasis. Okay, you might have heard of the term desert oasis. So oases are usually formed in such depressions in the desert. Okay, where due to deflation the depression was created, the hollow was created, and if it intersects the water table that is prevalent in that area, it can form an oasis in the desert region. The next kind of landform feature that we see, which is credited to the wind erosion, is called the desert pavement. As we explained deflation, okay, so it will take up all the it will lift all the finer sediments, and it is going to take the finer sediments ahead with it. Okay, so with time what is going to happen is the land surface is going to get lowered. Okay, so suppose this entire area has been lifted off. Okay, then after some time even this area is lifted off, not the bigger grains, okay, but the smaller finer grains. So the amount of finer grains is decreasing, the level, the the land level is also decreasing, and the concentration of coarser grains is increasing. So after some time what you are left with is just the coarser grains. Okay, and this is then called a desert pavement. Okay, so it will be a surface composed only of the coarser grain fragments that cannot be transported by the wind over there. Okay, so these are called desert pavements. Now there is another kind of feature that we see which is associated with wind erosion, that is a desert varnish, or it is also called rock varnish. So what is going to happen is that sometimes the rocks are not sometimes the rocks are exposed to the surface after all the finer grains and everything has been moved away by the process of say deflation. So these rocks now which are exposed to the surface, okay, they might have some minerals in it which contain manganese, iron already. Okay, so due to the exposure to the surface, due to the temperature variation, and maybe suppose there might be some chemical weathering also that is taking place in these areas, these surfaces are going to get covered by a layer of, say, oxides of metals like manganese and iron, or the minerals like orthoclase or microcline. These will start getting disintegrated and to or changing the chemical composition to clay minerals. Okay, so all these kind of material, all these kind of say oxides or clay minerals, okay, so they get deposited over the surface of such rocks which are exposed due to the wind erosion that has happened. So they are going to that entire layer that is now there is called the stain. It is usually darker in color, okay, and it is going to be glossy also, the way it appears. Okay, so this is called desert varnish or rock varnish. So this is also a feature which is associated with wind erosion, where because of wind erosion the rock is it has kind of got exposed to the atmosphere, and because of weathering and erosion and chemical changes in chemical composition, is going to deposit a layer, a dark layer, glossy layer, which is called a desert varnish. Now there are as we explained that one of the processes that happen when erosion with respect to wind is happening is called abrasion. Now because of abrasion, a feature called ventifacts are formed. Ventifacts are actually, they are suppose you see a rock exposure, okay, and you see that the surface of this rock has a lot of cavity kind of features in it. So these cavities are formed due to the rock getting abraded and etched and grooved by sand size sediments which are being transported by the wind. Okay, and these sediments are actually causing the abrasive action on the rock exposure. Okay, and usually these happen in places where there are no obstruction to these sand the sand that is being transported by the wind. Okay, so they are flowing with the wind at great speeds, great velocity. Okay, and when they meet the obstruction, there is sudden drop, will get rebounded, or it is just going to kind of scrape over the outcrops that are present over there. So that is how you will get ventifacts. Okay, so ventifacts are these outcrops which have kind of grooves or holes in them. Then another erosive feature is called the yardang. So yardang usually is found in areas where you have alternate layers of soft and hard rock. So what is going to happen due to the wind erosion? Okay, so your wind is going like this, and this area was actually covered by softer rocks. Then this area was also covered by softer rocks, and this area also. So due to the wind erosion, okay, so these areas with the softer rocks or less resistant rocks got eroded away, they got disintegrated. What you are left with are these long linear features, okay, which have sort of a little flat tops on top, okay, and these linear features are called yardangs. Okay, so this is again an erosional feature that is because of the action of the wind. Then you have another feature that is called a zugen. These are also kind of formed in the same way that yardangs are formed, but these do not make very long linear kind of a thing. Okay, you can see that it's not that long. Okay, these are isolated kind of mass, okay, of resistant rocks or hard rocks. The area around it was probably made up of softer rocks, so they all got eroded, and this was remaining over there, over here. So these are called zugen. So now we learned, how wind is actually kind of causing erosion to happen. Okay, and it is, picking up sediments with it. It is again with further erosion because of the sediments that is already there in the wind. It is causing more and more erosion and disintegration of material. Okay, so it is going to pick up that disintegrated material also with it, and it is going to move forward. So we need to know what sort of, there are few mechanisms with how the sediments get transported with the wind. Okay, so what winds do when they are blowing over a surface. Okay, once kind of once they are either laden with the sediments or they are not. Okay, so they will either lift the sediments with it and they are going to blow over. Okay, or there is going to bombardment, that is one sediment that is being carried by the wind. Okay, it's going to strike another surface, and because of that newer sediments are being splashed out of that area, or kind of broke apart from at that place, and then these sediments are also carried forward. Then these sediments again are going to uh, strike another outcrop or another sediment. Okay, and the next way that winds can transport is by dragging. It can drag the sediments along with it, along the surface of the earth also. So the processes with respect to the sediments are then called suspension, saltation, reptation, and surface creep. So what is suspension? Suspension is actually the fine, very fine sized sediments are actually picked up by the wind and carried by the wind. Okay, so lift, as we said. Okay, so they are going to get lifted and they are going to be carried by the wind. Okay, then the next one is the saltation. Saltation are kind of they are bouncing from one place to another. Okay, so they are temporarily lifted from the ground. At some place they are going to fall back. Okay, on the ground it is either going to strike another surface and then bounce back again carried by the wind forward. Okay, so that is how saltation happens. Okay, so they're just bounding from one place to another along the surface in with the wind blowing. What is reptation? So reptation is when the salting grains, okay, the saltating grains are hitting, suppose a rock surface. Okay, so it is going to, generate a few more sediments, or whatever finer sediments are remaining, are there on the surface. Okay, because it is hitting that surface, the finer sediments over there will get splashed. Okay, so how you can take a coarser stone, okay, any stone, and you hit in like any place which has loose sediments. Okay, you will see some parts of the sediments are going to kind of splash out of that place, or it's going to get bounce off that place, and then these smaller sediments, okay, can again be dragged by the, carried forward by the wind. So the next one is the surface creep. Surface creep is that these usually happen with coarser sediments, okay, which cannot be lifted off the ground, or they cannot even be lifted up enough to get the saltation happening. Okay, so these are actually pulled along the ground, pushed along the ground. Okay, so there are 2-3 coarse grains together in a line. So because the back one is moving, so it is kind of pushing the ones in front of it in the direction of the wind, because the wind velocity is enough for it to even move it along the surface. Okay, it can overcome the frictional force that is there between the surface and the sediment. Okay, and again saltation also helps in giving the momentum to these sediments which are dragging along the surface. So these are some of the ways how wind can transport sediments from one place to another place. So wind erosion we saw. Okay, so wind erosion is happening, it is creating the sediments also, and because of the created sediments also there is erosion happening. Then all of the sediments that is eroded is getting transported. Okay, so there are some factors which are going to affect the extent of wind erosion that is happening in an area. So firstly would be the aridity of climate. As I said before, if your wind is not very dry, if it has moisture, the erosive power of that wind is going to be lower. Then you have the soil texture. Again, the moisture content is going to be a factor. Your soil structure, the state of the soil surface, okay, and then you have the presence of vegetation, and then soil moisture again. So these are some of the factors that are going to affect the erosive power of the wind. Then there are some ways that you can characterize the desert environments. Okay, so what are the kind of properties, or how you can define an area as desert, is that it will have very low mean annual rainfall. Okay, so it should be less than 250 millimeters. Then vegetation is going to be very low or totally absent. It's going to have a very high daily and annual range of temperature. As we discussed before, the mornings are going to be very hot, like in the daytime, and night time it's going to be very different. Okay, so the diurnal temperature difference or variation is going to be very high in desert regions. Okay, you will see a lot of dust storms. Okay, so where kind of a lot of fine grained fine grained sediments is kind of uh, picked up by the wind, and because the velocity is so high, okay, and it's kind of blowing over a large area, it can create dust storms. And you will have obviously high velocity winds in those areas, and the dominance of sand sized particles or sand in general. Okay, so these are how you can characterize an area as a desert. Now there are some effects of wind erosion that we see. Okay, so wind erosion is not like how uh, in river, okay, when we consider the fluvial geomorphology. Okay, so whatever sediments that are there, okay, all of the sediments are kind of getting transferred by the river. Okay, so there, but winds selectively mostly carry the the finest particles with it. Okay, that is, if the wind's velocity is much higher, then it can pick up the coarser grains, and kind of it can drag those, or it can transfer those sediments to certain distances, not very large distances, but the finer particles that are picked up by the wind. Okay, so they can be transported over long ranges of distance. So these final particles are at a certain after a certain time, okay, these are going to get deposited. Okay, and when these depositions happen, they happen at large areas. Okay, so these areas are kind of closer, where in the regions where the wind velocity starts dropping down. Okay, so these will happen when the wind is kind of reaching at a place, okay, where the moisture content in the air starts rising. So what will happen, the velocity decreases, and the finer sediments also, which is carried by the wind, is you will start getting deposited in that area. Okay, so this fine sediment deposit that is happening, these are also called loess. Okay, so loess soil or loess deposits. Okay, and these are very fertile in nature, and these are very productive for farming purposes. Okay, and then also that another kind of the other landform which is created by the deposition of the sands is sand dunes. Okay, so we have obviously seen a lot of movies and videos where you see big kind of what to say, ridge like features, okay, mound like features, those are called sand dunes. Okay, so these are predominant depositional landform that is created by the sediments that are brought by the winds after erosion and transportation. Okay, and these can kind of move also, these can get built upon, or they can kind of shift from one place to another depending on how the wind is moving in an area. And these dunes can be large enough to kind of bury places, also bury your oasis, and also ancient cities, some civilizations due to any sort of also involvement of the tectonics in that air, or kind of a change in the wind blowing patterns over there. Okay, so a huge amount of, say, sand was kind of picked up by the winds over there because of the great velocity that it is blowing with, and it can dump the sand on the civilizations or cities, and it can just bury them. Okay, so these are some of the effects, or these are some of the consequences that we see after erosion and transportation has happened by wind. So now we will understand the sorts of landforms that are created, okay, by the deposition of the sand sediments that are being carried, that are being brought in by the wind. Okay, so some of the features that are characteristic of aeolian deposits. Okay, so you might find say dunes even in coastal areas. Okay, but there is going to be some difference in the dunes that are there in the coastal areas and some in the desert areas. Okay, so or maybe in, say, some are ripples. Okay, ripples are kind of landform that can be formed in both water prone regions as well as by the wind action. Okay, so but there is going to be a bit difference in the sort of sequences that are formed. So in sandy aeolian deposits, or the the wind driven landforms, okay, that are there, so it might have irregular cross bedding. Irregular cross bedding is like, suppose at one time the sediments got deposited like this. Okay, so they have got deposited like this, but this was the direction of the flow of the say any agent. The cross bedding is also formed by water flowing at a place. Okay, then you will see that the sequence kind of changes, and this is how the beds are getting deposited now. Okay, you can see that there is a change in the direction. Now these cross bedding could be regular or irregular. Okay, regular as in there is some form of symmetry, or there is a equal interval of these cross beds being forming. Okay, but for aeolian deposits, or the aeolian geomorphic deposits, okay, so these cross bedding are going to be irregular. Okay, because the direction of the wind could change at any at any time. It might be because of that, or because the sand that is deposited, it could be carried forward again because of the difference in the velocity. Okay, maybe the velocity of the wind changed, it increased, so the sand which got deposited first on the top, it might get dragged and deposited ahead. Okay, so you are going to lose that one bed. So that is why this gives rise to the irregular cross bedding, and these deposits are usually gently dipping. Okay, because the wind is blowing over kind of these are flat areas mostly. Okay, so there is no sudden elevation changes. Okay, so these are mostly usually gently dipping. Okay, and it could be steep and orient in different directions. Gently dipping, as in that the windward side is going to be gently dipping, and even the if you see on an overall, maybe you will see a lot of sand dunes. Okay, so you will not see a lot of difference in the heights of the dunes. In that sense, these are mostly gently dipping, and the other side of the these dunes are going to be steep, and the orientation of these other slopes or the other side faces could give you an indication to what sort of dunes are being formed over there. Okay, and because of that, you can also understand whether this area has a lot of change in the wind direction. Okay, so some of the examples of such depositional aeolian landforms are going to be ripples you have sand dunes, ergs, sand sheets, sand shadows, loess and takis. Okay, so we are going to learn about some of the most common ones. Okay, in the it has already been taught in the content and even today. So first we'll understand what are sand ripples. Okay, so these actually occur as a result of larger grains accumulating as smaller grains are transported away. Okay, so suppose you have coarser grains and smaller grains. Okay, all are being transported at one place. Suppose the coarser grains start kind of depositing. So what is going to happen with the wind is still moving like this, okay, and the uh, coarser grains are going to start getting deposited here in a linear fashion or some place else again over here. Okay, so these linear kind of features, okay, and they are like kind of forming in this fashion. So these are called sand ripples, okay, and these are always perpendicular to the wind direction. Okay, so this is the axis of and this is the wind direction, so it is perpendicular. What are ripples? Ripples are actually forming on the surface of the dunes itself. Okay, so these are small waves that are created. Okay, and these are not static. Okay, these are kind of moving along the wind direction. Okay, and suppose there is a windstorm or there is a sudden increase in the velocity of the wind, so these will kind of they can be just disappearing also. All of the sand that is there on top which were forming the ripples might get just lifted off from that place and transported ahead. So these are usually common in the windward slopes of the dunes. Okay, and there is something called windblown dust. Okay, so these are sand sized particles. Okay, so these are a bit coarser also in nature. Okay, so but these coarser ones will not travel larger distance. Okay, but the ones which are finer, okay, they can be suspended in the wind for a very long time and they can travel with the wind for large distances, and when the concentration is a lot and it is over a large area, okay, so it is going to just appear like a dust storm. Okay, so the wind blown dust is also kind of how dust storms are formed. Okay, so that is also one of the feature. Then we come to the most important depositional features that are associated with aeolian geomorphology. They are dunes. Okay, so these are classic aeolian landforms. Okay, so dunes are mostly of this structure. Okay, like this, then this. Okay, like this is the side profile, and a lot of them form in one place, and you have seen in obviously in a lot of pictographic representation or even visual representation of how large dunes are being formed at places. Okay, so usually they are stable, but there are some dunes which can advance along with the in the wind direction, or they can get reshaped as and when the wind changes its direction. Okay, so they usually originate in small sand accumulation like mounds. Okay, and they are not they might have got deposited from the sand which was blown out from one say depression. Okay, or a lot of sand is being carried and then probably the wind decreased in the velocity. Okay, so it might have deposited over there. So these are some of the ways that the dunes start forming. Okay, the windward slope is going to be gentle for a dune. Okay, and the leeward slip face. Okay, so if you consider this as your dune, okay, so this is your windward side and this is your leeward side. This is also called a slip face. Okay, this is called a slip face. So these are usually gentler in nature. Okay, gentle angle. Okay, these are steeper. Okay, you can see the differences. So the windward side is gentler in nature and the leeward side is the steeper one. Okay, it usually migrates in this direction, that is in the direction of the wind. Okay, so the wind is going like this. Okay, and if the dunes are migrating, they are going to migrate in the direction of the wind. There are two classifications that are used for dunes. There are free dunes and then there are anchor dunes. Free dunes are usually, they are the ones which are which can, move from one place to another, migrate from one place to another, or change their shapes. Okay, so you have transverse dunes, seeps, star dunes, zibars. Okay, so these are examples of free dunes. Anchored dunes are usually, they are anchored by the existence of a topography or vegetation. Okay, suppose there is kind of vegetated land, it's holding on to the sand deposit over there. Okay, so the dune has formed, the vegetation is there, so the part of the dune that is held by the vegetation is not moving, but the sides of the dunes can move. Okay, so examples of that are, parabolic dunes, coastal dunes. Okay, so these are some of the most common examples of anchor dunes. So the types of dunes that are, most commonly seen are Barchan dunes, parabolic dunes, transverse dunes and longitudinal dunes. Okay, so we will go one by one for these dunes. Before that, as I showed in the, kind of previous slide, this is the direction of the wind. Okay, so this is a windward side, okay, which has a gentle slope. This is the steep slip slope or slip face, as we call. This is the leeward side. Okay, and this is the crest of this dune. Okay, so these are the features of a dune. Now, how sand dune kind of, migrates and forms. Okay, so first this kind of, gentle windward slope is there, and, over here you have formed the slip face has formed. Okay, so as the wind is flowing, it will pick up the sand from here, and when, this area is kind of, devoid of the surface, the land surface is, lower over here, it is going to start depositing the sand that it is bringing. Okay, so if this was your original kind of, sand dune structure, sand dune shape, with time you will see that this is going to get lowered, the surface, because the sand from here is still getting eroded by the wind. Okay, and you see that the slope has now become gentler and gentler on the windward side. Okay, so this slope has become gentler, the height has also lowered. Okay, the crest was over here, now it is over here. Okay, and the sand is getting deposited ahead. Okay, sand will get deposited here, then again here. Okay, you see the crest is also moving, and the this is also getting gentler, the windward side. Okay, so this is how sand dune, forms as well as migrates ahead. Okay, from one place to, from, it will look like it is, kind of just stretching ahead. Okay, so one of the as I said, most common type of dunes that we find are Barchan dunes. So these are actually asymmetric crescent shaped desert moons. Crescent is nothing but this, kind of moon shaped. Okay, if you look from the top, it is going to look like this. Okay, asymmetric, why? Because, these two, areas are not totally symmetrical. Okay, so this part will have your that steeper slope. Okay, you can see here, this is the slip face, this is the wind direction, this is the slip face over here, and the dune movement is going to happen in the wind direction. Okay, so the sand over here is going to get eroded and then it is going to get dumped here, so this is going to be your new dune. Okay, then again with time it's going to go ahead, it is going to form a new dune. Okay, so this is how the Barchan dunes also migrate. Okay, these are isolated usually. Okay, so you will not see a chain of these. Okay, so these are isolated, they can freely migrate from one place to another and they will maintain their form, they are not meeting any obstruction. Okay, so which is going to change the orientation of their formation. Okay, and the characteristic features are their wings. Okay, so their wings are kind of, like this. If you see, these are top view. Okay, and they are going to maintain these kind of wings. They are not very long also in nature. Okay, and the windward slope is long and gentle, as you can see over here, and the steep leeward slope is the slip phase. Okay, and usually they range in heights of 1 to it can go from 1 to 15 meters, and sometimes they are very, they can reach tall heights, when there is a lot of sand supply, and the the sand dunes can move uh, across the area, like, there is large area provided for that. So next we come to transverse dunes. Okay, so these, as you remember, they were kind of type of the free dunes. Okay, so these are linear in nature. Okay, and these are usually forming ridges of sand, and the ridges are perpendicular. The crest, okay, this is the crest of the transverse dunes. Okay, so these are perpendicular to the wind direction. Okay, so the sand supply is there. Okay, and the sand actually does not move like this. Okay, so the sand, the long ridges are actually formed because there is a lot of sand supply in the lateral direction also for the transfer dunes. Okay, so these can occur in beaches, floodplain, um, alluvium. Okay, now if there is, stronger wind over here, what is going to happen at some places where, the kind of there is a trough over here. Okay, so what is going to happen, the sand over here starts moving ahead, and it can form Barchan dunes with time. Okay, like one over here, then if you see another trough over here, so the sand will, start arms will start forming, and this area remains here, but the sides will then get converted into Barchan dunes. Okay, so this is one aspect of transverse dunes that can happen. Okay, then you have another dune, that is the dome dunes or domes. Okay, so these actually don't have slip faces, but the transport of the the orientation and the transport of sand is, kind of similar to the transverse dunes. Okay, you can see over here. So these are the domes. Okay, so maybe the wind side is this side. Okay, so they are not like linear in nature. Okay, but the sand, when it goes, it can, kind of transfer the sand here, because it's over here, there is a, kind of uh, what to say, obstruction over here, so some of the sand supply can go here. Okay, so that is how even domes could be, type of transverse dunes. Okay, and then you have reversing dunes. So this is your wind direction previously. Okay, uh, the slip faces that are there, okay, it's going to be on the opposite side of the crest. This was your crest. Okay, so this is your crest. Okay, this is your slip face, this is your crest. Okay, for reversing dunes, the slip face could be on this side. Okay, this is in response to, wind coming from two opposing directions, and they are, as I said, okay, but they will be classified as transverse dunes because again the sand supply is going to be perpendicular to the, the crest. Okay, right angles to the crest. Oh, sorry, this is going to be there. Yeah, Kuldeep. Actually, I think I said it wrong. Okay, the sand supply for transverse dunes is going to be in the, perpendicular to the crest, that is in the wind direction. I'm sorry, I, explained it wrong. Okay, Kuldeep, you had a question?
Yes, ma'am.
Yeah, say.
So the ma'am, only difference between transverse and longitudinal dunes are their direction,
Yeah,
right?
yes, yes.
Okay, okay, ma'am.
Yeah.
And the formation is the same.
No, no, I'll come to that. As I said, I explained it wrong. The sand transport is going to be in the direction of the wind for transverse dunes, but they create these linear kind of features. Even longitudinal, it's going to be linear in nature, but the wind direction and the transport is going to be a bit different from the transverse dunes. I'll come to that in the coming slide. Okay. So yeah, so that is one correction over here. Okay, so the sand transport is also like this. Okay, sand transport is actually right angle to the crest. So this is your crest, and the sand transport is, you know, perpendicular to the crest. Okay, so just keep this in mind. Okay, now we come to the longitudinal dunes. You can see over here that these are also linear forms. Okay, and they are parallel to strong persistent winds. Okay, so your wind direction is like this, and you see the crest is in the direction of the wind. Okay, in transverse you saw that the crest is perpendicular to the wind direction. Okay, so this is the difference between the transverse and the longitudinal dunes. Okay, so I hope Kuldeep this clears your doubt. Okay, uh, these are also called sieves. Okay, because they are, you know, they have sharp edges also. Okay, and they have irregular sand supply. Okay, you can see it is not, you know, totally symmetrical or kind of, you know, regular in view as when you saw transverse dunes. Okay, so the sand supply is irregular. Okay, and there is some shifting of the wind direction also. Okay, so that is the longitudinal dunes. Star dunes are actually formed in places where the wind direction has no predominant direction. Okay, the wind is not flowing in a predominant direction, and it usually happens in areas where there is the vast availability of the sand, and it is, you know, it can form like this. Okay, this will be the crest, and then after a while this will start forming. So you will have one, you know, two arms like this, and these arms are not regular. Okay, they can be irregular. You can see that they are, you know, not even linear in nature. Okay, and you can have a lot of, you know, edges and crests over here. Okay, so this is how star dunes are forming. They can grow in height because, you know, because of the sand getting transported to, you know, the middle of the star dune. Okay, or the center of the star dune, it can grow, keep growing in the height. Okay, it can just get built upon. So that is why it can grow much greater in height. Now we come to parabolic dunes. As you remember, parabolic dunes are the part of the anchored dunes. Okay, so what happens is these vegetation start forming on the dunes. So this area is not going to get eroded. Okay, the sand over here maybe, you know, can flow, but this cannot go further, much further, because the vegetation is obstructing the flow of it, or it's holding on to this sand. Okay, so what is going to happen, the arms are going to get longer. Okay, this is where all the sediments are going to get transported and deposited. These usually form in subhumid and semi-arid because, you know, because there is precipitation over here, the chances of vegetation growing over here is higher. Okay, so usually they initially originate as blowouts. You know, suppose this area was, you know, there with which had coarser grains as well as the finer grains. A blowout happened. Okay, so as I remember, if you remember the example that I gave, like if you blow on the powder, you will see there is kind of a concave kind of feature that is formed, and the powder has moved ahead. Okay, so similar nature. Okay, so the sand from here has gone over here. Okay, and the vegetation has occurred. Okay, so now the wind direction is over here only, but this area is not getting kind of eroded, or the sand over here is not getting transported. Whatever is happening along these arms. Okay, so this is the head of the dune that is formed due to the kind of the blowout that initially happened. Then there are another kind of smaller sized mounds or dunes that are formed due to the effect of vegetation holding on to the sand, that is called napka. napka or nepka. Okay, these are also called as shrub dunes and hummock dunes. Okay, so these are anchored by plants, and those areas, they remain, they are not shifting or migrating anymore. Okay, so whatever erosion or transportation is happening around it. Okay, so they appear as mounds in desert areas. So this was about the kind of the aeolian geomorphic processes and the different kind of um, different kind of landforms that are created because of the occurrence of uh, the winds blowing over the earth's surface. Usually these, as I said, these are characteristic of areas where the climate is very dry and hot, and there is less vegetation, and the sand supply is much more. Okay, so most of the sand size particles or finer particles are transported over larger distances, okay, by wind, and then they you get such big depositional features. Okay, so the dunes that actually form, they kind of they um are spread over very large areas. Okay, so the desert areas that we saw, okay, they are containing kilometers and kilometers of area. So the sizes of these dunes are can also be that great. Okay, so obviously the proportion of aeolian landforms is lower than what we saw with respect to the fluvial landforms, but still they are very important for us to know. Okay, and as we said that because the sand getting transported in areas, okay, they can bury a lot of features, okay, maybe previously formed geomorphic features or any tectonic features. Okay, so because of their aeolian geomorphic processes, a lot of burial can happen. Okay, a large amount of sand supply can take place and it can bury a big area. Okay, and later on with time the sand can get uh, okay, Kuldeep, you can share your screen and ask if you have a question.
Okay, ma'am. Ma'am, let me show you something. Okay, so are these longitudinal dunes? It is in Mexico. No, no, it's in Utah, United States.
Uta, okay.
So are these uh, longitudinal dunes?
Uh, these are in arid regions, right? So like
Yeah, yeah.
are we classifying them as dunes? These are classified as dunes because
Actually,
sometimes you
no,
can
ma'am.
also get linear features on ground because like this, okay, because of some lineaments being present. So these are canyons, right? This is in
Yeah.
canyon regions. So canyons are formed due to fluvial activity.
Oh, yes, ma'am.
Yeah, so I don't think you can classify these as dunes. See,
Oh, okay.
again, the environment also matters. Okay, so if this entire area is created by fluvial systems, then the occurrence of dunes can be there. But since this is such a hard rock terrain, I don't think you will get dunes per se.
So, ma'am, longitudinals are not that hard.
See, dunes, any sort of dunes are mostly made up of sand only. So, hard rock you cannot get with sand.
Okay, so these are sorted materials,
These
fine
are
grains.
actually sedimentary rocks which have been formed much in the past. Okay, and the fluvial system has actually cut through these rocks and they have formed canyons. Dunes are made up of sand, okay, they are not made up of rocks. What we saw as yardungs and all, they can be hard rocks because they are erosional features. Depositional
Okay, ma'am.
features by wind are usually sand only.
Ma'am, can I ask you about canyon formation? Something like.
I shared that Google form, na? So you put these doubts in that also. I can cover these
Okay,
together
ma'am.
when I'm summarizing the entire content in the revision session, because
Okay,
there
ma'am.
is some part left even today's content, so I want to finish that off. Okay.
Okay, ma'am.
Yeah,
Yes.
I have a
Saurabh,
question.
yes, you have a
Yeah,
question.
yeah.
Yes.
I have one question which says that since you said that winds are selective in nature, probably they erode the lighter material or the finer material, right?
Yes.
So if we think from the oil and gas reservoir point of view, so I
Okay.
think fluvials are the one who produces good reservoirs,
Yes.
and aeolian will not be able to produce the good reservoirs because they
No.
normally do it with the finer material, right?
Yes. See, the thing is,
Okay.
it also depends on the kind of sediments that are getting deposited. See, all the finer material, okay, that
Mm-hmm.
is getting deposited by the air or the wind per se are going to be dry in nature. There is no moisture in it. Okay, for something to get compacted, okay, and when you say fossils are getting trapped in the kind of clayey sediments, okay, and then they are getting compacted, okay. So because of that the organic matter is increasing, right? The fluvial system has more organic matter than what you would find in aeolian deposits.
Okay. So even in that case, if alien deposits basically they convert into rocks, right? If they
Yes,
go through this process of
yes, yes,
deposition and
yes.
then compaction, so even if they do, if even if they go in that way, so looking at the size of the particles and the fine grained material, I think they will not be a good reservoir from oil and gas point of view,
No, I
rather than
don't
the fluvial
think.
one.
No, they won't be very good reservoirs.
Okay.
They could be maybe cap rocks later on, like there
Yeah.
is some reservoir
Maybe.
down and then it got buried by the sand and then sand got,
Precisely. Yeah.
yes. So the porosity is there, but since
May
it's
not be permeable.
yes, so
Okay.
that could be one of the reasons why they will not be good reservoirs. Very interesting
Hmm.
question. Nice.
I work in oil and gas company, so that's why
Oh,
I'm
okay,
thinking in
okay.
that way.
Okay, okay. No, no. Obviously, then you will have to think about in the application sense. Okay, so I'll go back to my screen sharing. Okay, so as we said that sand or the aeolian processes can carry a lot of sand and dump it at a place and it can bury large areas. So one of the places that we see the influence of this as well as the interaction of tectonism is actually in the Kutch area. Okay, so the Rann of Kutch, as you know, it kind of forms in the arid region. Okay, so it is dry and there are a lot of aeolian deposits also present over there, but it is also seismically active. Okay, now seismically active, but it is not at a plate boundary. The area that we deal with in the Kutch region is actually an intraplate region. Okay, so it is actually uh, a lot the distance, or it is much further away from the plate boundaries that are existing between the Indian plate and the Eurasian plate. Okay, so that is 300 to 400 kilometers away from the plate boundary. Okay, but tectonics are very active in this region. Okay, and the tectonics are active because the continental collision is still happening. Okay, and we see far field effects in the Kutch region. Okay, but there should be some driving mechanism also, which is giving rise to these tectonic activities. So you can see in this tectonic map that there are a lot of faults, okay, that are present over in the Kutch region. Okay, so what happens is that because the earthquakes that have occurred in this region have been studied, okay, the Alaband earthquake or the Bhuj earthquake. Okay, so what they realize that some of the faults along which these tectonic events are taking place are actually kind of were not known before. Okay, they are termed as they are termed as blind faults. Okay, blind faults as in there is no manifestation of these faults on the surface. You cannot structurally map these, or you do not see any traces of these faults on the surface. So these are blind faults. Okay, so with later on studies, they kind of realized that there were some faults which were not seen before, which they did not know about, and because it's in the intraplate region. Okay, so in intraplate region you would in general sense you would not expect seismic activities. Okay, but Kutch is one such intraplate region where this happens. Okay, so what is the distinction between an interplate earthquake and an intraplate earthquake? So interplate earthquake is those that is happening between the plate boundaries. Okay, so whatever earthquakes are happening in the Himalayan region, okay, so that is interplate because it is between two plates. Intraplate are the earthquakes that happens in that one tectonic plate itself. Okay, so in the Indian plate like Kutch, then you had I think Latur earthquake also in Maharashtra. Okay, so these are examples of intraplate earthquake. Interplate, the recurrence time is less because why? Because this area is already active, right? So the collision is happening, or subduction is happening at that place. So it is seismically very active. Okay, so the recurrence time of the earthquakes is high. Okay, but in intraplate the recurrence time is longer. Okay, so the interval between the two seismic events is going to be very long. So it is also a bit difficult to monitor such intraplate earthquakes. Okay, because the duration is so long, you cannot really predict it very well. Okay, you don't know where the slip is going to take place. Okay, so that is a bit difficult to understand. So interplate earthquakes are recognized at surface. You can see the fault surfaces. Okay, you can obviously you can see the traces. You can see the features associated with such faults and earthquakes on the surface. Intraplate earthquakes are, as I said, rarely recognized on the surface. Okay, so the faults are kind of buried under several kilometers of surface materials, and because of the longer recurrence intervals, the expression of the faults may be kind of eroded. Suppose there might have been some trace of it or some feature with respect to one old earthquake event, but because the recurrence interval is so long, these areas might get eroded because of some, say, fluvial system, or another some kind of deposit has taken place and it has buried the traces, or it has been eroded away. Okay, so these are some of the issues when we try to study or try to interpret the intraplate earthquakes. Interplate earthquakes release less stress and are dissipated quickly because of weaker rocks near the plate boundaries. Okay, so near the plate boundaries, since the tectonism is active, okay, so the deformation of the rocks at the boundaries is very high. Okay, and because the deformation is high, it kind of already consists of weak material. Okay, weak rocks. So when the earthquake is happening and the stress is released, okay, so the amplitude or the kind of the effects of the earthquake waves, that is, it is absorbed by these weak zones. Okay, it is absorbed and it will get dissipated. Not always, obviously we have seen a lot of when the magnitude is very high. Okay, so it is very damaging, it is very disastrous, but as in the plate boundaries, okay, even small scale earthquakes are consistently happening, but we do not see a lot of kind of effects of these because the stress is absorbed by the weak zones or the unconsolidated material that is present in such plate boundary regions. For intraplate earthquakes, these can release stress, okay, and because the ground motion caused by such earthquakes is, it will not get absorbed very quickly, owing to the, kind of strong coherent rocks that are present over in the interior of the, tectonic plates. So, like, most of the areas where these intraplate, like if you consider Latur, okay, so Latur falls in that, Deccan province, okay. So, that is one, kind of, it's one uniform rock, it is resistant rock, okay, in that manner, okay. So, the ground motion over here cannot be absorbed by any unconsolidated sediments that are present, okay, and the seismic energy, they can transfer or, transmit over longer distances in the intraplate earthquake scenario, okay. So, this is these are the differences between the two types of earthquakes that are, usually classified. So, what happens in Kutch is actually part of the intraplate earthquakes. Okay, intraplate earthquakes are very disastrous, very dangerous. Okay, you cannot predict them, and you don't know, which faults are there because they are buried, as we have already mentioned. Okay, so um, that is why tectonic geomorphology and such other morphological features, okay, they can, interact together and form such, areas where you can, find no trace of such faults, okay, and intraplate earthquakes can take place in these faults. Okay, so first we'll consider the 1819 Ran of Kutch earthquake. Okay, so because of the this earthquake, okay, with the magnitude range from 7.7 to 8.2. Okay, this was very these are like extreme earthquakes. This also caused tsunamis. These caused this earthquake caused uplift of an area as well as the depression of an area, and the uplift and the depression. Okay, the effects on the topography of that area was very distinct, okay. So usually what happened over here was that the subsidence created a lake called the Sindri lake, and the uplift, okay, that happened caused damming of a river, okay. This is a natural dam that was created because of the uplift that happened during the Ran of Kutch earthquake of 1819. Okay, so the maximum displacement during the earthquake was estimated to be 12 meters. Okay, so this they have understood by the measuring the height of the bund, that the dam that was created, and the subsidence of the area where the Sindri lake was created. Okay, so the lateral extent of this entire deformation area was around 80 kilometers. Okay, so that is why it was a, kind of moderately high uh, magnitude earthquake. So over here you can see that this is the scarp, okay, that formed. Okay, so this area got uplifted, okay, and this area got subsided. You can see the Sindri lake has formed here, okay, and this is the uplifted area. This has, kind of it caused the formation, or it caused the damming of the river, okay. So the rivers that are mentioned is Kori or Nara, okay. So these are the most obvious effects, the topographic effects, okay. These could be all, this is kind of an example of the tectonic geomorphology that we had also spoken about in the previous one of the live sessions, okay. So this was the most obvious topographic effect, and it was, kind of a ridge you can see over here, okay. So this was a thrust fault, okay, a reverse fault, a thrust fault, where the hanging wall has moved on top and the foot wall moved down, okay. So this was the area that got subsided, and this was the, kind of the scarp that developed, okay, and then this was the uplifted area. Okay, so this is how your this kind of topographic variation happened because of the displacement along this fault. Okay, and because of this earthquake, okay, because of the movement along this fault during this earthquake, later earthquakes also received, the consequences happened because of this earthquake. Okay, so the 1956 Anjar earthquake was due to the reverse faulting, which was similar to the 1819 fault. Okay, and this similar, because of this, and the changes in stress caused by the Coulomb stress transfer due to the 1819 earthquake may have been sufficient to trigger the 2001 Bhuj earthquake also. Okay, and further studies reveal that there were some historic, very ancient earthquakes also which have taken place in this area, okay, which were not known before. After these earthquakes took place, okay, that's when after doing paleoseismic studies, people have realized there were ancient earthquakes also that have occurred in these areas, okay, and which kind of resulted in the disintegration of few ancient civilizations also. So we'll see that also. Okay, so this Allahabad earthquake, or the 1819 Ran of Kutch earthquake, actually gave, okay, Coulomb stress transfer. Actually there is a kind of criteria that we consider when we are talking about the stress. Okay, so don't focus on the word Coulomb right now. So the stress transfer is that during when this displacement happened, okay, after the displacement happened, so that time the stress got released. Okay, now again the movement along these faults keep happening, okay, but they do not release the stress every time that okay, so the stress keeps building up, building up, building up. Sometimes what happens is maybe the stress got released in this area, okay, but the effect was not seen in the area where the stress got released, but the effect of that stress happened at some other place. Okay, so the Bhuj earthquake, what we will see in the next slide is that it actually occurred along a blind fault. Okay, so we did not know that fault existed, but the stress that was being released by the displacement in this area, okay, or the stress that was released from this area, some part of the stress got transferred and it stayed along the fault where the Bhuj earthquake will take place later on. Okay, so the stress got built up. Okay, the effect of stress traveled from one place to another. Okay, how you can see this is that suppose you are pushing two blocks together. Okay, so the stress is only on the interaction between this place. Okay, but it's not just over here. This entire block is also experiencing stress. Okay, the stress is building up in this intersection also, but the stress is still there in the entire block. So maybe the some part of the stress is released from here, but this area still has that stress. Okay, and the stress keeps building as this is still moving. At some point the stress over here, okay, at the back of the block has increased a lot, and this place will get displaced and the stress will be released. So that is what the stress transfer refers to. Okay, when we are considering big tectonic plates, okay, so collision in collision of Indian plate with Eurasian plate, okay, the stress is there at Himalaya also, but there are effects of that stress even further away, kilometers and kilometers away from Himalaya also. Okay, so the stress can travel. So that is what we mean, that because of this earthquake in 1819, some stress was developed. It got transferred. It was building up at the area where Bhuj is also there, where Bhuj is there now, and later on the stress got released, and due to which the earthquake happened in Bhuj. Did you understand the concept of this? I think
Yes,
Pooja.
ma'am. Yes, ma'am.
Okay, okay. So now we come to the 2001 Gujarat earthquake. Okay, so which is also known as the Bhuj earthquake. So the epicenter was actually, the actually the kind of, yeah, the epicenter only, it was pretty deep. Okay, so this was a very deep focus earthquake also, and the magnitude again was moderate, 7.6, but the intensity was extreme. Okay, so as I said before, that this earthquake was caused by a movement on a previously unknown south dipping fault. Okay, there are a lot of rift kind of features. Rift are what these are kind of rift basins or rift structures that we say. Okay, so these a south dipping fault which is parallel to the rift structures. Okay, so south dipping as in the fault plane is kind of dipping towards the south. Okay, so this is your Bhuj. This is where the epicenter of the Bhuj earthquake was. Okay, so it was an unknown fault. We did not see it. There were no traces of it which were studied before or even observed on the surface before. And even after the earthquake, there was no major surface rupture associated with the kind of the earthquake that happened, the displacement that might have occurred along that fault when the earthquake took place. That's why it's called a blind thrust earthquake, or it was on a blind thrust fault. Okay, so the other effects of this earthquake was the lateral spreading and strike slip faulting. Okay, so that occurred because of the the displacement that happened along this fault, which caused the Bhuj earthquake. So this is how you can see that old geomorphological features, maybe the deposits, the Ran of Kutch deposits that have happened. Okay, so that has kind of buried the faults that have been created over there because of the ancient collision between the Indian and the Eurasian plate. Okay, so one factor is that. Then one tectonic movement that happened during the 1819 Ran of Kutch earthquake, which was an intraplate earthquake. Okay, because of that, the other thrust fault systems or other fault systems that are present got activated during that time. Okay, because they got activated, they might have not released the stress at that point of time, but the stress buildup started increasing. Okay, and we don't know where these faults are, because some of them are hidden. And then later on, the 2001 earthquake, the Bhuj earthquake, that gave us the confirmation that there are some faults which are hidden in Ran of Kutch, and these are also prone to earthquakes. Okay, the intraplate earthquakes. So when people started studying, after the Bhuj earthquake, okay, so the studies, okay, they are done with respect to archaeology also, as well as the geological and the geophysical aspect. So what they found was there were several moderate to large earthquakes which have taken place in this area. Okay, so either in the recent times as well as in the past. So one of the oldest, or you can say the ancient earthquake that happened was around 2700 BC, that is the Dholavira earthquake. So Dholavira is actually part of the the Harappan and Harappan civilization. Okay, so that with studies they found that Dholavira earthquake had happened, which was around 6.5 in magnitude, okay, around in the time 2700 BC. And the decline of Harappan civilization was then associated with calamities like floods and these such earthquakes. Okay, because of earthquakes there was obviously disruption, there was destruction, and maybe because of that the decline of Harappa civilization started. So earthquake hazard, as we see even in the modern times, it's one of the major causes of the destruction of any kind of settlements around that area. So based on the scarp morphology, it was suggested that the 1819 event occurred along a buried north dipping thrust. Okay, again the the fault along which the 1819 earthquake happened, even that was buried. Okay, And the paleoliquefaction features, we will come to what is the liquefaction features. Okay, in the 2001 earthquake also suggests that Kutch was hit by similar magnitude event around 800 to 1000 years ago. So that is when the 2700 Dholavira BC Dholavira earthquake studies came into the forefront of research. So over here you can understand. Yeah. So what the study found was that you can refer to the paper with the reference that I have mentioned at the bottom of the slide. You can read the paper if you are interested. Okay, so around 2600 to 1600 BC, there was damage to the Harappan settlement at Dholavira, okay, which is around 60 kilometer north of the epicenter of the Bhuj earthquake. Okay, and this kind of gives an idea that the earthquake which destroyed the Harappan civilization is related to such fault systems that are found in the Rann of Kutch area. Okay, archaeological records have suggested that Dholavira was struck by a major earthquake around 2200 BC, as it is evidenced by displaced vertical walls, bulging and tilting of walls. These are kind of the things that we observe now when earthquakes happen. We observed in the constructed properties. Okay, so they have correlated that with the kind of constructions that are still remaining in these areas. Okay, and they have also seen that the civilization, the people that stayed there, they had also done repairs to these constructions. Okay, then this was archaeological records. Okay, with geomorphic analysis, people have found that the central portion of the Kutch mainland fault got activated during middle to late Holocene. If you remember, Holocene is the kind of the most recent period in according to the geological time scale. Okay, so the geomorphic features that they kind of studied to understand whether there was kind of any effect with the earthquakes that have happened was river gradient changes in that, development of fault scarps, okay, offset of drainages, strath terrace development and ponding within a river channel adjacent to a fault plain. We have talked about all of these in the previous content. You can refer this slide and see how these geomorphic features form when there is a disruption in the kind of the present state of the geomorphic processes. Okay, so the river is forming. If there is an earthquake, there is a kind of shift in the area. Okay, so you will see that the river has changed its sinuosity, or it has changed its direction. Okay, and suppose there are the terraces that have been formed. Some terrace got buried because there was flooding. Okay, so if you take the ages of the terraces, you can realize which terrace formed first and which terrace formed later. So did that place undergo subsidence or uplift, okay, as per that. So this is how geomorphic analysis can also help you in understanding the archaeological perspective of such areas, okay, such archaeological sites. It can tell you whether any sort of natural disasters affected or influenced the decline of such big civilizations of the past. Then you also have the evidences of fallen debris and bulging and slumping of fortification walls. Okay, so these are also associated with occurrences of earthquakes. So that is why it indicates that in 2200 BC, around that time, okay, earthquake did happen, and it is evidence from the different kinds of what we say the deposits that you find, or kind of features that you find, or kind of fallen construction elements that we find in such areas. One of the ways where which is one feature that is helpful in understanding the age of the earthquake or kind of denoting the time to certain earthquakes is by studying sand blows. Okay, so this is actually part of the paleoseismology. It's a branch, okay, that is there. So actually Javed sir, Professor Javed is himself, he works on such paleoseismic things. Okay, so what are sand blows? Okay, these are patches of sand that erupt onto the ground when waves from a large earthquake pass through wet loose sand. Okay, this is actually what we were talking about, liquefaction. Okay, so the sand kind of uh, it starts behaving like a liquid, okay, when an earthquake happens. Okay, so the sand is there, okay, it starts kind of it interacts with the groundwater level, groundwater that is suppose pushed up, okay, due to the earthquake. Okay, it interacts with the sand, and the sand itself will start acting like a liquid after that. Okay, it becomes wet, the loose sand, okay, because of this. And when the pressure increases a lot, it's kind of spills out on top of the surface. Okay, so the sand grain kind of starts flowing out of the surface, and it will form a feature that is called sand blows. Okay, now if you suppose as you can see here, okay, if the age of the material buried by the erupted sand can be, if you can understand the age of this, okay, if you can date this, okay, and this is on top, this has buried this, okay, then you can say that the earthquake has occurred after this date. You can date this, okay, and this area which is buried by the sand blow, okay, so the earthquake has happened after this time, okay, after the this silt and sand, silt and clay layers, okay, you can date this. And after the earthquake has happened, this sand blow has taken place and it has buried this. But if you see that the sand blow itself is buried by a layer, okay, and you are dating this now, okay, if you are dating this, and this is the age of the sand blows is more than the sediments that are burying the sand blows, okay, so the earthquake has happened before. So these kind of buried sand blows can give you information about past earthquakes. Okay, so this is how we use such features which are associated with earthquakes, as well as kind of the burial mechanism that takes place with respect to geomorphic features. Okay, so that is what we can use these features to understand paleo earthquakes in the region, and then we can understand the paleoseismic nature in that region. Another kind of tool or the method that we use is trenching. So paleoseismological trenching, it is an important tool where we can understand or study past earthquakes, okay, and we can try to predict the present or future behavioral characteristics, okay, and these are obviously clubbed with other what to say, earthquake monitoring techniques, and where we can kind of use it to predict. So the aim of trenching is actually to expose the stratigraphical and the structural features that are buried in a place, okay. And the modern deposits have kind of buried all the older signs of such seismic events, and if we do the trenching, we can find one cross section, okay, where you can see all the layers, all the features, and then you can compare the older or paleoseismic features with the modern day features. Okay, so there will be some changes. Right now it is still, suppose, okay, so presently there is no activity, and in the past there has been activity. So you can see the kind of variation between them. Or if in the past it was kind of in a static state, okay, past it was calm, but recently there has been some seismic activity, again there is going to be difference in the features that we see. So trenching is a tool where we can compare the features and distinguish the features that are with respect to the modern day or the still kind of scenario to the seismic events. Also we can understand the history of the fault segments, and we can develop that where the location and the magnitude of future earthquakes could be there. Okay. And so trenching is actually it could be used in seismic risk assessment also. So again, the purpose of trenching is to understand or expose the rupture geometry and the style of the faulting. Okay, you can understand whether it was a normal fault or um, reverse fault that has happened. Okay, when you do the trenching and see the layers or the stratigraphic uh, stratigraphic layering in that area. Okay, obviously stratigraphy and also the complete depositional history we can find out using the trenching method, or any other buried feature. Suppose you see that sand blow kind of a feature. Okay, or the buried river gradient changes or buried scarps. Okay, so trenching will help you in getting that also. So to reveal the slip history, okay, with respect to a fault while we are doing trenching, there are some kinds of configuration of the trenches that we need to follow. So you need to have multiple trenches closely spaced, so you can see the amount of slip along all the trenches that you have created, and then you can understand the history of the slip. Then you need successive exposures. Okay, and these need to be dug orthogonally to the fault zone. And then you could have different types of fault parallel trenches on each side of the fault. Okay, so if this is a if this is the fault, okay, this is the fault, this is the fault scarp, and this is your fault. Okay, so we need two fault parallel trenches on each side of the fault. Okay, so we can see the offset features. Suppose this is trenched, and the exposed, obviously you are not going to see the subsidence or the displacement on the surface always. Okay, so one trench over here and one trench over here, this is your ground surface. Okay, so you will see that there is an offset in the stratigraphic relationship. So this is where trenching comes into use when we want to understand the kind of different features associated with older faults, or even faults which have happened, which are getting activated now, and we try to compare and we try to predict the future earthquakes if possible. So that is all for today. If anybody has any doubt till now, can ask, and I will again share the form in case anybody has missed it. Okay, please put in all your doubts. You can fill the form multiple times. Okay, and it is going to get saved for me, so I can take up the questions that you put over there, and in the revision class, obviously I will try to summarize things based either on the doubts that you have, or I will just summarize all the things that we have learned till now. Okay, so I hope that the content that I am giving itself is a good summary for the entire week's content that is already present in NPTEL, and you all can revisit the obviously the sessions that are already uploaded on the YouTube. So you can clear your doubts before the putting your doubts over here also. So anybody has any doubt for today's class can go ahead.
Like, not a doubt, but I would say, like, can we have this form on this NPTEL notification which they give to that
Okay,
individual
I'll
login and
put it
for
on
the,
the discussion forum, because actually that is not a
yeah.
part of the NPTEL team as such. So this is my
Hmm.
personal thing. So I'll put it as on the discussion forum. So
Yeah, that's
the
fine.
yeah, so the mail will go to everybody who has joined the discussion forum. Okay,
Yeah, that would be fine. Yeah.
and I'll also put it in the the Google Doc of these slides that I have there that I've put. Okay, I'll put it right in the title slide of this week's live session. Okay.
Okay. Okay.
Anything else?
No, not doubt in this one, but pretty doubts in the older lectures probably. So I
Yes,
need to
sure.
write
So
them.
just keep putting them, and I'll prepare the content as per those, and I'll explain everything at that point of time.
Okay.
Okay.
Thank you.
Thank you so much for attending. And if nobody else has any queries, so I'll end this session. And if you have any queries after you go through the session and the content again, so please put your queries in the Google form. I will put it, I'll send the message right after the class, so everybody will get it. Okay. So thank you for attending. Hope to see you in the next week's lecture, which is going to be a revision session for kind of everybody who is giving exam, or if you just want to get the entire summary of the the course that has that has been taught to you. Okay then. Thank you. We'll see you next class.
Thank you.